I love how it just gets the top of my head. That's how tall I am. It's great. Okay, so eye clicker. Okay. All right. Okay. Everybody click in on eye clicker. I think so.
Okay, I don't know.
Okay.
Probably.
That's fine. What time is it? Okay. So at least you have a test right now, right? Could be worse. Good luck on your exam next period, those who have instrumental. So today's joke, why did Mr. Potato have a cell phone? In case Mr. Onion rings. That was cute. What do you call a woman with fish in her hair? What do you call a woman with fish in her hair? A net. Or a net. Okay. Don't forget to click in on iClicker. Some people haven't done that yet. Okay. So we are talking facts now, right? Lipid structure and function. When is our exam? Tuesday. Tuesday is our exam. Okay. So let's before we do like actual slides and stuff, let's talk a little bit. Y'all know how soap is made? It's fats. It's fats. It starts out, soap starts out as fat. Now, what's the golden rule of solubility? Like dissolves like. So if something's polar, it will dissolve in something polar, right? Okay, so if soap is animal fat, what you have to do to that animal fat is you have to take it through a process called sponification. Sponification. ICAPON. What is it? What did I miss?
Sponification.
Thank you. Sponification. Okay. So in order to do this, you need heat. Not a hat. You need heat. Oh my God, it's hot in here.
It is hot.
I complained about it yesterday. And then you need a really strong base, something very alkali. So something like NaOH, you need KOH, something like that, really strong base, right? And so what's going to happen is that you'll turn that animal fat into what are called free fatty acids. And you're going to see them abbreviated FA. So what does that tell you about animal fat? Did you have free fatty acids in animal fat? No, animal fat is really triacyl glycerides. You know what glycerol is? Mm-hmm. Okay, so each carbon of the glycerol molecule is bound to a fat. And so it's no longer free, it's bound. And we're going to look at structures. So if that's like foreign language to you, it's okay. Just know that it's bound in the animal fat form. And then when you go through sponification, you get free fatty acids. So you don't just get free fatty acids, you get free fatty acids plus you get your whatever metal you had, right? So sodium, potassium ions. So you get basically salts. right? Because these are both charged, so you get them as salts. So when you do this, if you have these free fatty acids, this is in your soap container, right? If you just put soap on your hands, nothing happens, right? What do you have to do to make the soap work? Add water and you have to rub it together, right? You have to give it a little bit of energy, right? So what's happening to those free fatty acids when you do that? What's the deal with a fatty acid? A fatty acid is what kind of a molecule? Well, partially. Partially, that's true. Partially, it's polar. So partially it's polar, partially it's non-polar, right? So what do you form with something, and what do you call that? Well, it forms a micelle, but these molecules are amphipathic. AMPH, amphipathic? I don't know. Cool. So they're amphipathic. So when we scrub our hands, you end up making micelles. So that's great for soap, right? That has saved us as a civilization, right? Huge impact on life as we know it. But what happens if we have free fatty acids inside of the cell? Why is that not good? If I just told you make a micelle when you wash, what ends up in the middle of the micelle? Anything that's very what? Non-polar, right? If this is your free fatty acid, right? You got a polar head and a tail, right? And this is a micelle, right? If I want to wash fat off of my hands, right? Then I'm going to have my fat here and the tails are going to kind of associate. Oops, wow. I lifted the pen. That's terrible. So sorry. I really did lift the pen. Okay. So then you have fats that get stuck in the micelle, right? So the non-polar tails associate and we can wash the fat away. Yeah? Okay. So that's how I get fat off of my hands. You ever notice like if you touch butter or something like that, you know, you're baking and it's like all on your hands and you just rinsing it doesn't get it off, right? It doesn't. What do you have to do? You have to use soap. And the soap, all of a sudden, it quickly comes off, right? Why? Because you're trapping it into a micelle. And then all you do is run the water and it runs down the drain. So does soap kill anything? No, it just washes it down the drain where it goes to the water treatment facility and the water treatment facility will kill it. Right? Okay, so if this is what happens to fats on our hands, what happens if I had free fatty acids in my cell, in my body? Of what? Of all your cells, right? So do you know what has free fatty acids? Not us. Not us. Snake venom. Snake venom. What?
I've heard of that.
Yes.
It uses to break down the body's cells.
Free fatty acids. Why? Because it works as a micelle. We think of this action as a positive action in general, but it's not positive or negative. It just happens. And depending on your situation, it could be a good thing, it could be a bad thing, right? If it's running through your bloodstream, very bad indeed, right? You better get to the hospital. But if it's on your hands, this is a good thing. Isn't that kind of cool? It's kind of crazy. So I like to do this kind of just in the beginning so that we kind of have an idea of like why they're important. Yes, we're going to talk about like all kinds of different roles, but like I like to take it somewhere practical first. So cool. All right. So we'll talk about lipids, right? And lipids are made up of fatty acids. So we'll have to talk about basically the structure of fatty acids and then how fatty acids are put together to make lipids. Then we'll talk specifically about triacylglycerols, right? That's what tags, right? When I wrote here, TAG, triacylglycerol, right there, right there. Those are our energy storage molecules. So you can write TAG. What's that? It's one. If it's one, it makes a triglyceride, or it's triglycerols if you have multiple. Just it's plural and singular. And then we'll talk about what actually the cell membrane, because what you use for energy storage is very different than what you use for structure. And then we'll talk about cell signaling, which is another really cool, but very different mechanism. So as alluded to, right, lipids can look very, very different. And depending on their structure, they're going to give you different roles inside of the cell. So the triacylglycerols that we talked about, these are what are going to be for storage, energy storage, right? So they're going to give you lots of reduction potential because you have lots of saturated fatty acids here. And we'll talk about that. But you have unique lipids that are used in your cell membrane. And they have particular structures that give them the ability to make that lipid bilayer instead of just a micelle, right? You ever wonder why some of them make micelles, some of them make bilayers? Structure. Then we'll talk about all kinds of signaling within the body. The one you've probably already heard of is steroids. Eicosanoids are the other one, but they're both very important in endocrine signal. All right, so start simply. What is a fatty acid? Got hair. Ooh. So what? It is a hair. It's like in my face. So fatty acids. We have in any given fatty acid a carboxylic acid and a hydrocarbon tail. Can we draw that? Okay, what's a carboxylic acid? COOH, but that doesn't tell me structure. That's true, COOH, but that doesn't tell me structure. I have a carbonyl bound to hydroxyl, and then some R group, right? That's a carboxylic acid. So what is the hydrocarbon tail? We take the R away, and instead of calling it R, now we're just going to give it a hydrocarbon tail, right? And I just drew for a while, right? 4 to 36 carbons. You got a big range in there. So most of the ones that we find in the body are anywhere from 12 to 20 carbons long. And they're always going to be even numbered, and they're even numbered because when they're built, which we will talk about, they are built via 2 carbon units. Okay, this pen driving me crazy today. It's like I pick up off the screen and it doesn't register that I picked up off the screen. So via 2 carbon units. So we can use these fatty acids to build different parts of the membrane, things like that. We can also covalently attach them to proteins, right? So if you have a lipid that's embedded in the membrane, we can link a protein to it and therefore anchor the protein at the membrane. Remember when we talked about all those cell signaling pathways back in Biochem 1? Why did some things stay at the membrane? Because they were tethered to certain lipids. And so we'll revisit those lipids. You'll be like, oh, I know you, all right? Okay, so there are multiple ways to classify fats, lipids. One of them is to classify if they are saturated or if they are unsaturated. So if you have something that is saturated, what kind of carbon-carbon bonds are you going to have? All single bonds. So this is going to be all. So what is the problem? All carbon-carbon. I'm going to write in cursive. Single bonds. All carbon-carbon single bonds. So what are they saturated with? Hydrogens, right? So what you should have are all fully reduced methylene groups, right? So 2 hydrogens per carbon in that carbon chain until you get to the end. right? The end's gonna have 3. How about unsaturated? At least 1 carbon-carbon double bond, but if you look at food labels, you've seen the mono-unsaturated and the poly-unsaturated divided into a category. So mono-unsaturated means that you only have 1 carbon-carbon double bond. Polyunsaturated means you have at least 2 or more. And they're actually going to have different effects on the body, right? So these long chain saturated fatty acids over there, those are going to be our energy. Because they're fully saturated, they have lots of reduction potential. Goodness, it's high reduction potential. I hate this pen today. If you have something that's unsaturated, these are going to be the ones that are found in membranes. Okay, so just so that you kind of have an idea of what's the difference in structure and function. The more saturated you are, the more we're going to use you for energy. The more unsaturated, we're going to use you for membranes. So if we look at some of our common fatty acids, one of the things you have to be able to relate, you have to be able to look at the structure and know how it's going to affect the melting boiling points of the different lipids. So do you remember, like, I don't know what's the last chemistry you did this in, but intermolecular forces, do you remember intermolecular forces a little bit? Yeah. So fats really have that non-polar area and the polar area, right? So the polar head groups over here, this carbonyl area, these can undergo what kinds of interaction? If you have the hydrogen associated, you could do hydrogen bonding, but typically in physiological conditions, that hydrogen's kicked off. So you end up with dipole-dipole interactions. But what about this fatty acid tail? London dispersion forces. So what happens in London dispersion forces when you compare something that is a straight chain versus something that is not straight anymore? It does have to do with branching. Like if you took a straight chain and you used the same number of carbons and you turned it into branching, what would happen? So let's talk about forces first. So this is how I think about it. I think about it like a book, right? When you buy that perfect new book, how are those pages in the book? And they are perfectly straight and they line up, right? And so you can have lots of London dispersion forces because those electrons can get really close to one another, right? So you can have lots of interactions there. But oh no, you brought your book to the bathtub to read, right? While you take a nice long hot bath and you drop the book in the bathtub. One ruined book. But what happens to the pages? They get all wrinkly. So does it ever fold back in the same space ever again? No, and that's what these are, right? So what's the difference? Sorry, y'all. So what's the difference between the ones up here? These are all what? They're all saturated. Therefore, they are straight chains. Okay, so now we go from those to these. These are all monounsaturated and polyunsaturated. Which ones are more funky looking? Are polyunsaturated. So the more carbon-carbon double bonds you have, the less intermolecular forces you're going to have. So look at the difference in melting points, right? We have a melting point here at 54 degrees Celsius. I go to a mono unsaturated and I go down to 1 degree Celsius. I go polyunsaturated, I am -5. So you have a huge difference saturated to mono and then a smaller difference from mono to poly. okay? So when we look at these, you also have to understand the designations, right? So if you look after, look at palmidate right here. So we say 16:0. What does 16:0 mean? See if I can zoom in. Let's see. So yes, it tells you, whoa, no, that was not what I wanted to do. There we go. Okay, view, zoom. Let's do this. Okay, there we go. Now we can look, it's a little bit bigger. All right, so if we look at palmidate, this is telling me the first number is telling me I have 16 carbons. Where is carbon number 1? It is the carbonyl carbon, right? That's number 1. So I have a thinner line here. Here we go. Then we count 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 16, right? That last one is 16. So it's the number of carbons in the chain, including that carbonyl carbon. And then the 0 tells you that you have no double bonds, right? So go down and look at oleate. This is 18:1. 18 carbons with 1 double bond, but you could have multiple fats that have 18 carbons and 1 double bond, but in a different configuration, right? So you actually have to say, where is that double bond? So you do that in parentheses with a triangle, and you number the carbon that is the first carbon participating in the double bond. So I have to start counting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are the carbons that participate in the double bond. So the first one participating in the double bond is number 9. Have y'all done this before with fats? No, right? No. Okay. Just want to make sure. So now, the other thing that we have to worry about, do you see some of these? Every time that we see a double bond, we also have another designation. And in all of these, it is what? Cis. They're all cis. What does the cis refer to? So this is so in this case, because it's a long chain fatty acid, all we're looking at is the parent chain. You don't have to look at substituents or anything like that. We're just looking at the parent chain, right? So what effect does having cis or trans bonds have, okay, on the molecule itself? So if you have something that's completely saturated, right? And we introduce either a trans double bond or a cis double bond, you're going to have a very different effect. If we introduce a trans double bond, what I'm looking at is the parent chain. The parent chain is going one way on one side of the double bond, and it's going the other way on the other side. They use the hydrogens as like visual representations of that, right? So if the hydrogens are going in opposite directions, so is the parent chain. But the hydrogens do not determine if it's cis or trans. It's the parent chain. Okay. So then look at cis. Cis, we're going in the same direction. Yeah. Okay. Look at the structural difference. Which one is more like the book that we dropped in the water? Absolutely the cis. Absolutely the cis. All naturally occurring unsaturated fats are in the cis configuration. You noticed on food labels, they separate trans fatty acids from all trans fats from all the other fats. So the only example in nature of forming trans fats is when bacteria ferment milk products and things like that, like when you're making cheese, you're actually going to make some trans fats in that process, but no organism makes trans fats for their use. So we don't have enzymes that are designed to metabolize trans fats. So that's why trans fats are a big outlawed thing. But think about why would the food industry make so many trans fats if they're so bad for us? So talk about state, right? If I have things that are cis, what's going to happen to my melting point? It's going to go down, right? So they're going to be more liquidy. What's going to happen if I have more trans fats? Melting point is going to be higher. It's going to be more solid, right? So the two things are the state of matter that it's in, whether it's trans or cis, and the shelf life. If we have more trans fats, it's going to last longer on the shelf, but it's not good for us, right? It's kind of an interesting little side note. Okay, so y'all know how they get trans fats through a hydrogenation reaction? We talked about this when y'all took lab last semester, well, whatever semester you took it in, right? We talked about hydrogenation and how if you start with something that's got a double bond and you hydrogenate it and turn it into a saturated fat, if you do it chemically in the lab, it's not always a complete process. And so sometimes when you start with something that's in the cis configuration and we start dropping hydrogens on that double bond, right? You lose the double bond and you turn it into saturated. But some portion of those saturated molecules will actually re-lose those hydrogens, and they could either end up in the cis or trans configuration. So you usually end up with a mixture of a hydrogenation. So you start out with this mono unsaturated, you do a hydrogenation reaction, and you get both of these products. So that's why you get trans fats, because they just happen. So if you look at the foods that we eat, right? If I said at room temperature, what is your butter like? It's a solid. At room temperature, what is your olive oil like? It's a liquid. Where do you get olive oil? From olives. Olives are plants, right? What? Yeah, that's an example. So if you look at plant lipids, right? Plant fats, what you're going to see is that they have a low melting point. So at room temperature, they're going to be liquids. But butter, where does butter come from? Animals, right? And all of this, if you like a nicely marbled steak, right? At room temperature, what is that fat like? Solid. So why is that? Well, look at the structure. What do you have more of in one of them? I'm not going to say which one. What do you have more of? So you have more saturation in animal fats than you do in plant fats. So plant fats have more carbon-carbon double bonds than animal fats. And it looks different, right? And it also has an effect on cardiovascular health, right? If you eat more saturated fats, you're going to have more cardiovascular risk than if you eat more saturated, unsaturated fats. Ooh. Is the better, yeah. It's still what?
It's like still eat it in moderation.
Oh yeah, like
Don't just go chow down on.
Yeah, that's exactly right. But there are some specific fatty acids that are linked to reduced cardiovascular disease. And these are our omega fatty acids. You've heard this, right? Fish, right? Everybody hears this, right? So what in the world does that mean, right? So when you look at any given fat, if you go from the other end, not the carbonyl end, the other end, the end of the molecule, right? What's the end of the Greek alphabet? Right, the alpha and the omega, have you heard that? Omega is the end, right? So the last carbon, the terminal carbon, farthest away from that carboxylic acid is your omega carbon. Then what you do is you count towards the carboxylic acid, and the first carbon that you reach that is participating in a double bond we call that an omega-3. It would be 3 away. An omega-9 would be 9 carbons away, right? And so what they found is that people whose diet includes these omega fats have better cardiovascular health. And they think it actually has to do with activating a nuclear receptor. And that nuclear receptor, right, those are transcription factors. And that nuclear receptor will change transcription. This is what they think, they're not 100% sure, will change transcription of lipid metabolizing enzymes. So not that the fat itself is better or worse for you, it's just prepping your body to metabolize what you are eating, if that makes sense. So these are all essential fatty acids. What's the difference between a regular old fatty acid and an essential fatty acid? Close. You can't make the essential fatty acid. There are many fats that are necessary for the body to function, not just these omegas. But we cannot make these omegas. That's why we must consume them in our diets. And we're going to see this with amino acids. We're going to see that common theme, right? Remember when we talked about all the different cofactors that were required and we called them vitamins and, right? Some that we could get in our diets and some that we couldn't. Well, some that we could make in our bodies and some that we couldn't, therefore we ate them, right? Same sort of deal. Okay, so if you look at an omega fatty acid, so the omega carbons all the way over here on the other side of the carboxylic acid, right? So you count inwards, and this is called an omega-3 fatty acid. But does that tell you about the entire molecule? No, you have many different fatty acids that can be omega-3 fatty acids, right? Alpha-linoic acid, right? Icosapentaenoic acid is another one. EPA. Have you seen DHA? You've seen this on vitamins and stuff, right? Especially like prenatal and like baby vitamins, things like that. They're like, oh, they market that they have these omega fatty acids. So this is docahexaenoic acid. So they're different, right? They're different numbers of carbons. This one's 18, this one's 20, this one's 22. What do they have in common? That if you go to the end of the molecule and you count in 1, 2, 3, that's your first double bond. 1, 2, 3, 1, 2, 3, right? Okay. You have omega-6 fatty acids. So you have to go all the way 6 carbons from the end. That's an omega-6. But you also have to be able to write their designation, their normal designation, right? So the 20 is telling you you have 20 carbons. You have how many double bonds? 4. Where are those double bonds? They begin at carbon 5, but be careful that you're counting from the carboxylic acid for these numbers.
For the count that first carbon on the right.
Yep. So for these numbers, you're counting from this side. For the omega number, you're counting from the omega carbon. Yep.
Do you think it's important to be able to look at the structure and say which fatty acid it is?
No, you don't have to be able to recognize it. No, 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 no. But if I give you the designation, can you draw it? Yes. If I give you the drawing, can you name it? Like, not the name, but can you give me everything else about it? Yes. Do you have to go and memorize lipids? No. But you have to be able to use the designation. And I'm going to give you an activity to do that in just a minute. Right? So that you can actually do it because you need to try. Okay. So that's actually what I want. That's exactly the point. So only do one side. One side's part 1, one side's part 2. We can't do part 2 yet, but we can do part 1. So in your book, if you can access your book, there's a nice little table. And it's not in here. Oh, it is. Okay. So these are a bunch of the different fats that are found in different food types, right? So if you look at saturated fatty acids, you can look at the percent of each of the common fats that are in, let's say, beef fat, right? Beef tallow, or in olive oil, right? And you can actually look at the combination of different fats, and you can see that they're composed of things that are more saturated versus things that are unsaturated, right? You can start to see those patterns. And so that's what you're kind of going to do here, is you're going to need the book so that you know what these different things are, and you kind of need this chart. Okay, so I'm going to let you try. Yeah, I'll leave the chart. Yes, I think it's somewhere in there. Yeah, we can go back. So first we got to be able to draw the fats, then we're going to be able to link them together and combine it like triglycerides and things like that, right? So you're going to pick any one of these food sources. I would absolutely pick one that's in the book. It's going to make this activity a whole lot easier for you. And this is posted on Moodle if you want to download it. It's cool. So there's a little part for you to do on your own. And then the pair and share is once you've got something on your paper, then I want you to turn and talk to your partners. Mm-hmm. Okay. Mm-hmm. But draw the most common. Don't, if you pick a food source, don't pick one that's like 1%, right? When you're drawing it, pick like, if you pick cow butter fat, right? Pick the highest percent, which is like 29, 27, 12. It's going to make way more sense if you do that. And what is ND? Like they couldn't detect it. So it's basically like 0. Whatever's in, whatever, it depends on what you picked, right? Depends on what you picked. Yeah, just pick the highest percentage. So once you have 3, turn and see if somebody else has some and share. Yeah, you have to, the partner has to name whatever you drew. So whatever you drew, your partner names and predicts boiling point. What's that? And then go look it up. Like if I gave you a table, you should be able to look it up. Make sure you can draw it nice enough that I can grade it at some point. Not today, I'm not grading today's, but I'm saying like if I ask you to draw something on an exam, make sure it's neat enough that I can grade it. How's it going?
Like the name of the molecule, but not the designation.
No, don't put the designate. Don't put the name. Don't put anything. Don't let them have that. Like just draw your 3. Don't name it. Don't put the designations. And then when you trade with somebody, they're gonna label it.
Okay, so it's okay if like once we push the other person.
Now, yeah, once you get the other person's paper, label theirs. And then once you label theirs, like give the designation, then go find the name of the fatty acid, estimate the melting temperatures.
I just drew the molecule.
It's good practice. Don't do part 2 yet. Do part 2 in a minute. You got plenty of time. You're doing great.
I wasn't sure what I drew.
you were so nice. I said that was so nice. You were not on the chart.
Yeah. Well, no, I didn't draw them on the chart. I drew all of them on the chart.
Oh.
And one of the guesses was not on the chart. I was like, what? I was like, you can't do that when it's not on the chart. Yeah.
Yet. Just wait.
There we go.
All right, and then trade with somebody else and see if they can guess the food source. That one should be the easiest part because somebody already named it for you. You should be able to guess the food source. So y'all know why they name fats this way? Like pomade, where do you think we get that from? Palm oil, right? So they're all named based on where they come from, but some of the names are like Latin. And so it doesn't make sense to us, but it actually is their source of origin, which is kind of annoying, but. Y'all ready? Y'all shared? Good? Maybe? Need another minute? Yeah, everybody's been trading. Everybody's been trading. It's a quiet trade today. It wasn't a big discussion trade. That's okay. All right, you ready? Yes, no? Okay, one more minute and then we'll start. All right. So you can keep working on that. And there's a couple of problems like that at the end of the chapter too. But it should be, you can talk to the other people and say, did you get the right one? Because you know what you drew. So make sure you give them the answer. So what we already talked about was hydrogenation, right? These are the two slides that I skipped. But I sort of talked about hydrogenation before, but all you're doing is using hydrogen gas to get rid of the carbon-carbon double bonds, right? So now if you go from having something that was unsaturated to having something that is saturated, what happens to your melting point? It goes up because you have more of those interactions. You know, the other way to think about those London dispersion forces is if you have a bowl of spaghetti, right? That's a lot like a saturated fatty acid. How many contacts are those spaghetti strands making with each other? A lot. Now, what if you had a bowl of meatballs? Much less, right? And that's what happens when those molecules get really the cis carbon-carbon double bonds, is that they'll curl up, and so they have less contacts. It's spaghetti and meatball, or a wet book, whatever you want to think about. So this is what I was saying before. You take something that is a cis configuration, you go through commercial hydrogenation, and you end up with a saturated fatty acid, but some of those hydrogens will pop off and you'll end up with a trans, right? And we talked about this. Dairy products do have some trans fats because of the bacteria, but yeah, okay, very technical with that. All right, so now waxes. Waxes are kind of weird, right? They're very similar, but they're different. because what we have is basically a long chain alcohol. So if it were an alcohol, how would it be different? You have a hydrogen bound to the oxygen, right? So we have a long chain alcohol that's linked to a long chain fatty acid. So this is normally OH, right? So if we link the two, what kind of a reaction is that? We're going to lose, it's a condensation reaction. We're going to lose water and we're going to form a bond between the carbon and the oxygen, right? So what do we form? What is this new molecule? It's an ester. It's an ester. Right? So different waxes, depending on the length of their fatty acid tails, have different melting points. So they can either be liquid or they can be solid. It depends on the temperature you're kind of talking about. Beeswax, right? Beeswax is about, there are 3 different kinds of esters in there, but these are all fully saturated. So look, these are all fully saturated. You see no carbon-carbon double bonds. But you can also have some waxes that are oils, like jojoba oil is actually a wax. Isn't that kind of strange, but it's actually a wax. Jojoba, J-O-J. I don't know how to spell it.
Probably
Opiate, maybe jojoba oil, something like that, right? It's really a wax. They call it an oil, but it's actually a wax. But anyway, the other really cool kind of thing about waxes is sperm whales. Do you know about sperm whales? Sperm whales have a massive compartment, right? And that compartment contains a ton of an oil that is a combination of wax and triacylglyceride. And so they can actually control whether this mix is a solid or a liquid based on their body temperature. And so if they change it from being a solid to a liquid, this is how they change their buoyancy. So if it's a solid, then you have low buoyancy and you sink, right? You dive. If you raise the body temperature, then it turns into a liquid and then it increases the buoyancy and they float to the top, they rise to the top. Yeah, like totally cool. Weird side notes, right? Okay, so we talked about free fatty acids, right? But that's not how we keep them in the body because we can't. If we kept free fatty acids, we'd damage all of our membranes and we would all die. So we have to either sequester them with proteins or sequester them kind of some other way. And the way that we do that is with a glycerol molecule, right? So at each of these points is what atom? Carbons, right? So what is a glycerol molecule? It's 3 carbon long. And then what's normally on a glycerol? No, a glycerol, not a triacylglycerol. A triacylglycerol means that we have 3 fats. So this is a fatty acid, right? This is a fatty acid. This is a fatty acid. That's why they call it a triacylglycerol. It's just an OH. It's just an OH. So when you have this, we're going to undergo another ester formation, right? Because what do we have on a fatty acid? Right? And then we have whatever long chain, right? And then you have your glycerol that's going to have an OH as well. So what's going to happen? You're going to lose a hydrogen, an oxygen, and a hydrogen, and you're going to connect the oxygen to the carbon. And you're going to form an ester. So they call it being esterified. So we've done that basically in 3 places on 1 glycerol molecule. Yeah. Okay. So when you look at examples of the animal fat versus the plant fat, right? What you have are those fatty acids that y'all were drawing, but those fatty acids are linked to a glycerol. So usually we draw a glycerol just like this, right? Each point is a carbon bound to an oxygen. So if you look at an animal fat, are you going to have some saturation? You can, you absolutely can, but more of it is going to be unsaturated. Whereas if we look at a plant, what do we see? Every single one is sort of saturated, at least a little bit. So turn your little handout over. And the next thing is using your drawings of fatty acids from part 1, link them in an ester linkage to glycerol, forming a triacylglycerol. So then using that, can you predict what your boiling point or your melting point is going to be? And what is it going to be, a solid or a liquid at room temperature? Right? So whatever you drew on one side, put it together in a triacylglycerol on the back side. Or if it's easier and you have room, just put it on the front. I mean, I don't care where you put it, but link it together and turn it into a triacylglycerol. And then label it kind of like this. Sure. It's not adding them together, right? That would more like the average.
Okay.
More like the average. It's more or less the average. And then go and check, because if you've drawn one that's on the chart, it should be pretty close to the melting point that's on the chart, right? This chart. Oop, this one. Because you pick one of these, right? Now, the melting point is also going to be dependent upon the other things that are there, but you should get relatively close. Relative. Get close? And then show it to somebody around you just to make sure that you're drawing it right. You can share it with more than one person. Just like share your drawing. Do you have the right esterification, right? The order of them doesn't matter. The order of them doesn't matter. Not quite, not quite, because like you got to think there's not really a 1 and 3, right? 1 and 3 are the same thing, but 2's different. So you could put, typically these have fatty acid tails of differing lengths. Typically it's not all the same, but the longer ones can be in the middle, on the side. That can vary. That can vary. But it doesn't really matter which order you put them in. So you have a melting point for each of the individuals, right? So, yes. Well, no, the melting points for the individual fats are in the book. Like you can look at the individual ones, right? And then, like, no, you can't do that offhand. Like you go look at the book, and then you would take the average of them, and it should get close to what's in the table. But the table's more than 3 fats per. Whoop, I'm going the wrong way. The table is more than 3 fats for one food type, right? Do you see that? So you're probably going to be off by a little bit, but not too much. As long as you pick the highest percentage ones, you're going to be close. Does that make sense? Yeah. So you're close. I mean, that's close. Anybody far off in their calculation? Everybody pretty close? What's your actual?
Percentage times the.
Yeah, but there are other things there.
Yeah.
That's the only thing. There are other things there. All right, we good? Questions? So anybody ever notice how when you season food, if you season something that has a high amount of fat, whether it's any triacylglyceride, right? Whether it's saturated or unsaturated, if you season it, it is going to taste more flavorful than if you season something that has no fat. You ever notice that? Well, fats are tasty. Fats are very cetaceous, and we're designed to like that. That's the like umami flavor, right? But the honest truth is most of those seasonings, right, are hydrophobic. So what do they want to be dissolved in? They want to be dissolved in fats. If the seasonings are dissolved in fats, they are now able to bind to the taste receptors on your tongue, and you can taste them. So you could put the same amount of seasoning on something that has 0 fat, that has a lot of fat, and you're going to taste the whatever, cloves, the ginger, the capsaicin, whatever it is, you're going to taste it more if it's on a fatty molecule. Isn't that kind of cool? What? Capsaicin? That's on peppers.
Yeah, I was always like very confused on the pronunciation because I've only read it. So I was like,
Capsaicin. Okay, so we already talked a little bit about sponification, right? Soap making. So all you're going to do is take your triacylglycerol, right? Here's your 1, 2, 3 carbons, and then you bound your fatty acids, 3 different fats. And you boil it in the presence of some kind of really strong base. And that is going to separate the fatty acids from the glycerol. So you'll get free fatty acids in the form of a fatty acid salt and your glycerol. So if have you been in the, you have been in the lab. That's hilarious for me to ask that. You've been in the biochem lab. You've seen the bricks of soap. I think it was Dr. Marlowe who made those. Was it Marlowe? Yeah, yeah. So it's not that hard, right? It's really not that hard. And then you can use that soap because what is it really? Free fatty acids. So those micelles will surround your whatever your non-polar substance is, and as you agitate, it'll surround it, and then you wash it down the drain. So micellar water is not just water, is it? You know, all those they're charging lots of money, and they say it's micellar water. What a bunch of. It's not. Does water form a micelle? No. So there is something else in there that is forming a micelle, probably a lipid. Okay. No, not necessarily. No. But it's false advertising. It's just like saying that aspirin is a blood thinner. Is Gatorade, electrolytes, man, electrolytes, right? It's the same crap. Okay, changing gears. Now we're going to talk about now we know how to make a triacylglycerol. We're going to talk about how we're going to use them as energy storage, right? Depending on how they are packaged, they are going to have different destinations inside of our cells, right? So basically their primary use is for energy storage. They could be used for other things, but the primary use of tags is energy storage. Why do we use triacylglycerols instead of glycogen? Right, we have glycogen stores. So why wouldn't we just stick with glycogen? Why do we also need triacylglycerols? We'll say versus not glycerol, glycogen. What's that? Yeah, but you can secrete a hormone. Hormones, you can go for hours, right?
Does it matter that it's not or it's different pathways?
Well, it does enter in different parts of the metabolic pathway. So it does do that. But like think about structure. Just the structure inherent of a glucose molecule versus a fatty acid. How much potential, like how much can you go through the citrate cycle? Right? Remember how we talked about that last semester? If you run out of sugar, what do you start metabolizing? Fats, right? That's the whole point of a low carb diet, is that you'll start to metabolize your own fats. So we said fatty acids, remember, have a higher reduction state. So you're actually going to get more energy. What does that mean? It's a higher reduction state. You're going to get more energy per carbon. If you follow the whole pathway, you're going to get more energy per carbon in a triacylglyceride than you will in a glucose molecule, a glycogen. Also think about sugars have lots of hydroxyls on them, right? So what are they? Remember, like dissolves like. They're polar, so they're soluble in water. Are triacylglycerides soluble in water? No. These are hydrophobic, right? Hydrophobic. So they are not saturated by water, right? They're not covered in water. They don't like water. So they're actually going to have less mass per amount of energy. So you ever heard of you're going to lose weight and you lose water weight? Have you heard that before? What is that water weight? That water weight is the water that's associated with glycogen. So if you look at glycogen is like 65% water, right? Because it's soluble, it's covered in water. So you're not going to get very much energy out of this. You get about 6 kilojoules per gram. But triacylglycerols, because they're not saturated in water, you're going to actually get 38 kilojoules per gram. So glycogen will last you a couple of hours. How long do fats last you? Well, a typical person, about 3 months. About 3 months. Right? You can go 3 months without eating and just metabolizing your triacylglycerols. I wouldn't recommend it. No, I wouldn't recommend it. I wouldn't. Like, the thing is, you can go, it's 3 days without water.
3 minutes without.
Yeah, 3 minutes with it. That's it. I was like, there's a 3.
3 days without shelter. 3 weeks without.
I don't know what it is, but it's like you can go 3 months on fats.
I missed that question. I was like, uh-oh.
What's that?
So like whenever you're counting your macros and stuff, and they give you percentages, your fats are always way lower than your carbs and like your protein. So I was wondering, since they give you so much more energy, if that's why your fats are always so much lower when you break down your macros.
Yeah, because you don't need as much of it in order to get the same amount of energy. Absolutely. Absolutely. Yes. Yes. Right. It makes sense now.
Right.
Like all of these things, this is the beautiful thing about this class. I love because all the little things start to make sense. You start to incorporate it all. So I just love that this class pulls it all together. All right. So right. And that's what we said down here, right? Complete oxidation gives you 38 kilojoules per gram, which is a lot more than metabolizing glycogen. All right. So when we talk about the different types of lipids, you have to think that there are lipids that we are going to make and use in our membranes and things like that. And then there are triacylglycerides that we actually consume, right? So the fat that we eat is what we're going to talk about first. Choliomicrons. So this is fat that we eat. This is what happens to fat that we eat. Four minutes. Okay. We'll do this slide and then we'll stop. So when you eat the fats, you have to have something that is going to transport them to adipocytes, right? Because your body is always like, winter is coming. I need to prepare, right? That's what your body's like that all the time. The body is evolved in order to prepare you for long-term hardship, right? So if you have any excess calories that you consume, you're going to want to store them. So we need to, the body thinks it needs to store them. And the way that we store excess fats is in adipocytes, right? So the question is, how do we get those triacylglycerides that we consume to the adipocytes? And so this is actually how we do it. This is an example of a collection of different molecules that are going to transport our triacylglycerides. So if you look, right, kind of in the center, do you see the red ones with the little, you know what it reminds me of? Well, sort of, yes, but it reminds me of the Matrix, you know, with the little things that had that, yeah, you know what I'm talking about. You know what I'm talking about. Okay. So you have this, it's actually part lipid, part protein that is actually going to surround the triacylglycerides and take them places. Now, you can have triacylglycerides. You can also have some cholesterols that you transport in here as well, but you need to cover it in some kind of a lipid. The lipid that surrounds it is a phospholipid. So just like the phospholipid that's on the outside of your cell membranes, these little transport molecules are also covered in phospholipids. What controls the fluidity of our membranes? Cholesterol. So you have phospholipids and you have cholesterol. So the cholesterol are like the yellow circles. It's not really a circle, but okay, I'll give it to him. So this membrane, it's actually very, very reminiscent of a membrane because it has phospholipids, it has cholesterol, it has lipoproteins. So these are proteins that associate with lipids, ApoE, ApoC, ApoI1. You know, all of these are very reminiscent of our membranes. We have the same types of lipids. We have proteins there. We have cholesterol there. But the difference is that it's more like a micelle, right? And that it's forming that ball around the triacylglycerides that we want to take to our, oh my gosh, to our adipocytes, if I can remember that. All right, yeah. It does. So we're gonna follow the path of these particles next time. Not next time. Not next time. Next time you have an exam in here. Then a case study. So we'll have like part of class, you know, it would be half and half. We'll have half lipids and then we'll have half case study. Then we have Mardi Gras, right? And then we'll have another class. So it'll be, this is piecemeal. All right. Go, good luck on your test. And we'll talk about lipid metabolism. About what? Okay.
And I'll be free until 5.
Okay.
Yeah. Like so we don't need to rush.
I will text y'all because